Okay, in question 6 here, we're looking at geometry. And the first part of this question, I think you're going to need to sit down after you looked at this. I got this wrong the first time I did it. I got it wrong the second time I did it. It takes a little while to wrap your head around the English here. This is more of a challenge in terms of interpreting a sentence, just an English sentence, rather than it is so much about maths. The statement is that two angles are vertically opposite if and only if they are equal in size. Now what I've done is restructure that sentence. Another way of saying that sentence is if and only if two angles are equal in size, they are vertically opposite. In other words, the question is saying that if angles are equal in size, then they have to be vertically opposite. And that is not true. That is false. Because, obviously vertically angles are equal in size, but angles opposite each other in a parallelogram are equal in size, or alternate angles are equal in size. So it takes a while, I think, to really wrap your head around this. They're saying here that the angles are equal in size. Hence, because they're equal in size, the angles have to be vertically opposite. That's the order of logic here. So in this case, it is false. They do not have to be vertically opposite. If they're equal in size, that does not imply that they're vertically opposite. And in our justification here, I'm going to draw a little diagram here. You pick, right, just illustrate any pair of angles that are equal but that aren't vertically opposite. Like, for example, alternate angles or angles opposite each other in a parallelogram. So in this case, your answer, you should say that it is false. And the justification, there's any amount of justifications. I've decided to illustrate an isosceles triangle. I drew a triangle X, Y, Z. And obviously the base angles in an isosceles triangle are equal to each other. So I'm saying in the isosceles triangle XYZ, the measure of the angle A equals the measure of the angle B. Clearly they're not vertically opposite angles, so that proves that the original statement is false. Okay, in part B here, we're introduced to this diagram. Basically we have a rectangle, but the top of the rectangle has been extended onto H and joined back onto the base of the rectangle AC. We know a couple of angles, theta, so that's theta, and that's theta. We're asked to prove, using congruent triangles, that the distance from F to E is the same as the distance from E to H. So you should recognize here that they want you to prove that the triangle FED and the triangle EHD are congruent. Remember that congruent triangles have 3 pairs of equal angles and 3 sets of equal sides. In order to prove 2 triangles are congruent, we need to do SSS or ASA or SAS. Remember, there's loads of different ways of doing this. So go back over, we have a tutorial in geometry that just goes through proving triangles are congruent. So it's really worth your while going back over that. I'm going to write the solution on the next slide, but I want to just talk you through it here first. Basically, I'm going to find one side that these 2 triangles have that are equal to each other, and 2 angles that they have that are equal to each other. If I can prove they have a side and 2 angles that are equal to each other, that's what we refer to as ASA. It's angle, side, angle. And if 2 triangles have angle, side, angle equal to each other, then all the angles and all the sides must be the same. In other words, I'll be able to prove that the distance from F to E is the same as the distance from E to H. First of all, there's one obvious one, it's the side. The distance from E to D is in both of the triangles, so that's the first thing we're going to say. We're going to say the distance from E to D equals the distance from E to D because it's a common angle. There's another really obvious one. Both of them have a right angle. Both of those are 90-degree angles. So I can say FED is 90 degrees, and I can say HED is 90 degrees. Now, students often make mistakes here. You can tell which angles are equal and which sides are equal, but you can't just state it unless you're able to prove it. One thing that we're going to look at next is, since the whole thing is a rectangle, obviously that means that this distance here from G to H is parallel to A to C. Those lines are parallel. And in the presence of parallel lines, you should always be looking for alternate angles and corresponding angles. In this case, the thing you should be looking for are alternate angles. I want you to notice that angle here at B and this angle up here at H, they form that familiar Z shape. And since the lines are parallel, these are alternate angles. So we're going to be able to say that this angle has a measure of theta. So if that angle is theta and the angle here at F is theta as well, that's our second angle. So that's going to give us our ASA. We're going to be able to prove that the whole thing is congruent. Now once we've got that, we're able to say that the distance FE must be equal to the distance EH, the distance FD must be equal to the distance DH, and this angle must be equal to this angle. So let me just write that out clearly on the next slide. Okay, so let me just go through what I outlined there. Remember, to prove two triangles are congruent, we need three things that they have in common, but we can't use three angles, because remember, if all three angles are common, that just means they're similar triangles, but not necessarily congruent. So there's two easy ones. The distance ED equals the distance ED because it's a common side. It's in both of the triangles. The angle DEF equals the angle DEH because they're both 90 degrees. So we have two of them straight away. We have to do just a little bit of work to be able to prove the third one. What I said then is the angle DBC, that angle at B, equals the angle DHE because they're alternate angles. They form that Z because there's parallel lines there. We don't have to go into so much detail as to explain the parallel lines. Since the question said it's a rectangle, we don't have to, everyone knows that opposite sides in a rectangle are parallel, so we don't have to go into that much detail. But basically from this, we can now say that the angle DHE is theta. And since that angle equals theta, we can say the angle DHE equals the angle EFD, because this was labeled in the diagram as being equal to theta. And my justification there is that they're both theta. So we've A, we've S, we've A, that's our three things. We can conclude the triangles are congruent, which means that the side FE must be equal to the side EH. In the last part of this question, we're asked to hence find the value of the angle theta. Now there's a number of different ways of doing it, but I think the easiest way of looking at it is, in the previous proof, we were able to show that that angle there is theta. The angle at H is theta, and the angle at F is theta, which means that those two angles are corresponding angles, which tells me that the distance from A to F and from B, the line AF and the line BH are parallel. In other words, I want you to look at this four-sided shape ABHF. That is a parallelogram. That there is a parallelogram. In the original question, it told me the distance from A to B is 20, which means that the distance from F to H must be 20. So the distance from F to H has to be 20 because they're opposite sides in a parallelogram, and from our theorem, opposite sides in a parallelogram are equal to each other. In B part I, we proved that the distance from F to E equals the distance from E to H, so they must be 10 each. That distance has to be 10, and that distance has to be 10, which adds up to 20 and is equal to that. Now let's look at the full rectangle. The distance from A to C is 50. So if this distance here is 10, then I know that this distance here is 40. And if I have that distance, that's the thing I wanted all along. Because now I just have a simple, this is just junior cert trigonometry now. We just have a right angle triangle. I want to find the angle theta. I know the opposite is 90 and I know the adjacent is 40. Remember, if you're dealing with opposite and adjacent, you can just use tan. I can say that the tan of theta is equal to the opposite, which is 90, over the adjacent, which is 40. And to get theta on its own, you just get tan inverse of 90 over 40. And if you plug that into your calculator to the nearest degree, your answer works out as 66 degrees. So that's your final answer for B part 2 here.